Hello everyone and welcome to another video. This time we'll be starting exactly where we left last time, and I think we can in this episode implement optional custom allocators in our generic list implementation, right? So I've been thinking quite a bit about this, even for future usability. I have a few ideas, and I think that the best approach right now is to associate the optional allocator with the inside the struct itself, right? Associate it with a specific object, and not need to pass it around all the time, right? I think that's the most convenient and probably exactly what you want, because if we support multiple allocators per, let's say, list, then it's going to be a mess to free it, because then we need to free it, and if we want to remove a node, then we need to free it in a very specific case depending on what allocator we used for that node. So I'm going to use one allocator for the entire list, and that allocator needs to be optional, so we need to support like no allocator itself, and in that case it's going to use some sort of default allocator, right? So I think that the first thing we can do, let's actually just move the allocator implementation downwards. So we're going to copy this, actually upwards, not downwards, and move it up here, right? So we have our allocator in there. Then we need to define a list header, right? We need to define a list header, and this list header is going to contain an allocator header, right? So we can define the allocator header right here. And this allocator header is going to contain a function, basically a field that is a function, and this field is basically going to be a function that returns a void pointer. It accepts, I have some notifications for Java, whatever. It accepts the allocator itself and accepts the amount of bytes, size in bytes, right? I need to find a good convention for this thing. I think I'm going to start using like that, using it like that, and we can call it allocator, and this is going to be a pointer, right? A pointer to a function. This pointer actually needs to be there. All right. So this allocator header is going to need allocator. Is going to need to have this. All right. Okay, and now, well, but in that case, no, this is still going to work. I think I need to think very carefully about it, right? I need to think very carefully about it, because if we now add this allocator header that all allocators will need to have, let's say this is a header, I need to guarantee that this is properly initialized, right? So how can I do that? I always think about that in the future, so I don't waste too much time right now in there. All right, so we have this generic header that all allocators need to have, right? And I think that some of you are already expecting a certain thing to be done, and that is that the list header is going to contain an allocator header, right? It's going to contain an allocator header, and this is going to be well, is this going to be, it's going to contain actually a pointer, right? Allocator, right? So this is going to be our allocator. And now every single list that we create is going to have this generic list header, so we can call it header. And this header is going to contain the allocator, and the allocator is going to then enables us to allocate. This is actually allocates, right? This is an allocate function, not the allocator. We can also probably say, well, you can call it allocator header, it's not concerning. Alright, so moving forwards, so we define the list header that is currently only contains the allocator, and now we can probably define a function here at the very bottom, allocates, right? We can call it alloc. It's probably, yeah, let's call it alloc. And this is going to have this signature, right? So this is going to be a void pointer, and this is going to be alloc, and this is going to accept the allocator and the size in bytes. And if the allocator is defined, then we need to say allocator.alloc. We can cast it well, I'm thinking about if we should or should not do something like this. Well, let's do something like that, yeah. So this is going to be the allocator, right? So this is going to be the allocator. We need to type that struct allocator to allocator, and this is going to be have the alloc function. This is not a type name, it actually is, right? So where is it? Oh, because, all right, yeah, we need to call it in lowercase. So I think that the convention I'm going to use from now forwards is that functions and variables are going to use basically lowercase with underscores, and types are going to use camel case, basically with the first letter being an uppercase, right? I think that's a relatively decent convention, right? So this is going to be the allocator. Well, I don't know if I should call it header or not. Let's assume this is the allocator, right? So this is the header, and now we have this generic alloc function, and if the allocator is defined, right? If the allocator is defined, we need, and this is actually an allocator, right? We need to call allocator alloc, and we need to pass the allocator and the size in bytes, and we can simply return this, right? So we can inline it. If the allocator is not defined, then we need to use the default allocator, right? And the default allocator for now, and this is not going to be what you're going to use in the future, but for now I'm going to use just malloc, right? In the future we are actually going to have a custom allocator being the default, but for now we're just going to use malloc. And since I'm using malloc, I can say something like this. We can assert the results, and we can return the results. All right, so yeah, we can say something like that. So the list header is going to contain an allocator, right? And since I'm using this convention, yeah, I don't know, I don't like long names, but in this case it makes kind of sense. So I'm just going to say allocator header, and this is an allocator header, and this is an allocator header, right? So on and so forth. So this is the list header. We are going to contain the header, and now when the list is zero initialized, that is going to be always the case, or I hope it is. We may find a mechanism to always zero initialize the list when it is created. Then this header, this pointer is going to be null, right? And if the pointer is null, then we are going to use malloc. Otherwise, we are going to use the defined allocator. Okay, so now here when we call malloc, instead of calling malloc, we can simply call alloc, and we can pass list header dot allocator. Right. We can simply pass something like this. Right, so this should in theory be enough. I don't need to assert anymore because we are already asserting this whenever we allocate the memory, and that's basically it, right? We don't need to do anything else. And this is now complaining about something. Oh yeah, because I still need to wrap this list around parentheses, right? And this is no longer complaining. Okay, so I think that's basically what I wanted to do. And let's now check it, right? Let's now check if this is working. Right here. Right, and I'm going to compile and run it, and this is still working. Okay. So I think I'm going to start to move this into the specific module where it is going to be stored. So I can create a source folder, and then I can create base, actually base.h. So this is going to be the header file, base.h. So, and if so, this is where we are going to store all of our allocators, generic data structures, and like common code that is not part of the engine or part of the server or client or whatever, right? So we can start moving all of this into there, and this is going to be arena alloc, right? And we will need to have I'm probably going to use a single header file for now. I don't think it is worth it to split it into two files, one for header, one for source. So I can use the trick that most single header file libraries use, and that is basically to have a macro, and if this macro is defined, we are going to define the source, and in this case we need to move this here, and here we just want the signature, right? And here we are going to need a cert, so let me fetch a cert from here. So we are going to need a cert. We are also going to need a stdlib because of the malloc, right? Here we need a standard definition. Here we need standard definition. Alright, and let's keep moving forward. So this function is no longer going to be called arena alloc. I'm just going to call it arena alloc like so, right, to follow the convention we specified earlier. And then I can copy this code, and I can probably move it here, so I can delete all of this. right? So this is probably going to be more important. Then this can be defined here, and this needs to be now defined like so. And this, all of this code doesn't need to be here, so this can be private, let's say, right? So this can be private to the implementation itself. So this calls new region, this needs to be new region. We can modify this to be size underscore bytes to follow the convention. This capacity, blah blah blah. New region, and so on and so forth. So this minimum capacity can be defined, can probably defined here, right? Because it is specific to this implementation. I can probably mark this as static, right? Because this is not supposed to be used outside of this compilation unit, or well, I can do that later, right? I can refactor this now and do that improvement later. So we have these type definitions, right? I don't know if I like this name, allocator header, to be honest, because I like short names, and so this is the function, right? I can call it allocator, I guess, right? I can call it allocator. Alright, I can simply call it allocator and then do this like so. Okay, now we need to modify, or actually copy this list header, and we can simply copy all of this exactly. So we can copy all of this. We can define the list implementation below the allocators, and this is going to be allocator. And instead of calling it list header, I can simply call it list to follow the convention we defined previously. Okay, so this actually is not tab aligned. Okay, so I think that's everything for here. This is working exactly as previous because these are all macros, and I think that's everything we can have for now in our base header. Okay, so I can have simple comment here saying allocators, and here I can have collections, right? Collections and allocators. And instead of calling it here, because these are actually options, so I can probably call it options, right? Can probably say this, but I deleted it by mistake, so I can probably say options and then use the optional allocator, and here I don't need anything. Alright, so now the problem that I'm seeing, I can probably test this code, is probably a good practice. So let's include base, and let's define base implementation. Alright, so we can define base implementation, and let's compile and run, and this should, because, alright, so I can move the u.c to source, and I can modify my compilation script to go to source, right? So this should be okay. So I have an error here, so in line 35, because this is now arena underscore alloc, same here. Alright, so let's go there. Okay, so everything is working as expected. So now I probably want to create a demo file so I can test, or I can actually demonstrate the behavior of this base header file. So the first thing I want to do is probably list, right? And I want to, actually I can say demo.c, and I can simply say include source base.h, can have exit success, right? I need to include standard lib and standard IO, and then now I want to start creating specific demo functions, right? So the first demo function I want is a list demo, right? So this is going to be a list demo, and for this list demo I can probably just printf list demo and have this be a new line and this be a new line. Actually something like this, right? So we have list demo, and now inside the list demo we can have a specific demo for the list demo. So we can say list declare, and we can declare something similar to what we already had, so a float list. So this is a list of floats, and we can declare something like a string list, and this is going to be a sharp pointer, right? And here we can simply say float list float list. So I can say floats, it's going to be zero initialized, and here I can say list append floats and pass, I don't know, 1.7. I can do the same thing we have here, right? So I can simply copy paste this code. Okay, this is going to be floats actually, and I can say list for and to reverse the floats in this manner. Why is it complaining? Oh, because false identifier. I think I'm going to not use false, I'm just going to use 0 for now, because it's probably better since it doesn't depend on an extra library, right? So we have float here, and I can probably just print them. Alright, so I can probably just print them. It's going to be it dereferenced. So then I can have a new line, and I can also probably say floats is equal to that, right? That we are going to print. No, I'm not going to add anything, right? Now I also want to demo that this specific macro list for supports nested loops. So I want to add a string list. So I'm going to say strings. Once again, this is still initialized, and I'm going to append a bunch of stuff. So I can say this is demo. I can say list demo, and here I pass the list we want to append it. And now I can print this inside that. Okay, and this is actually where is it? Okay, a reference. Okay, And there isn't much I want to say besides this, besides printf here, and I can say strings is equal to that, and I can probably add like a few spaces in here, and this is going to be it, the iterator, and here I can probably say floats is equal to something completely different, and I can say reference to it, and I'm going to specifically add this call here at after this second list for, just to demonstrate that this iterator doesn't get overwritten by this this nested for, right? So we can say something like that. And I probably think that's everything for now for the list demo. So let's compile it and run. So instead of compiling source demo, source du, I want to compile demo slash demo.c, and this is going to be demo, and this is going to be demo, and this is an implicit declaration of assert because I have not yeah, so I need to define base implementation. Okay, and I probably want to also include here because sometimes we are going to use the library without defining the implementation, so this needs to work in those cases. So I want to include assert here, not at the bottom, right? Not at the bottom. Alright, so that's everything. So let's try to compile it once again. This did in fact compile, and I need to call list demo here. Okay, so once again, alright, so this is the list demo, and why? Okay, I don't want to add this, and I probably want multiple new lines in there. Yeah, so I can say traverse list, and here I can say nested well, yeah, nested list loops. Right, I can say loop list or something like that. Actually, list loop. Okay, so if now I print this, it should be a little bit prettier. So I have the list demo, list loop, this is prints all of the floats. So I have nested list loops, and this prints all of the nested stuff exactly as we expected. Alright, so now I probably also want to add a few new lines in here and here at the bottom as well, so probably 2 new lines, and this should be already properly formatted. Okay, so we have a few cases, the list loop and nested list loop, and we probably don't need anything else for now. Now I want to have a demo for arena allocator, right? So we want to introduce the concept of the arena allocator, and in this case we can simply copy what we already had, like so. So created an arena, we say arena alloc, and we allocate 3. So here I can say, actually I want also this to be prettier, so I can say arena allocator demo, like so. So we allocated 3 integers. I don't need these, so I can say int. Yeah, I can say int 3 after int3 alloc. Right, I can say that. So after the int3 alloc, I'm going to have this pointer. I can say pointer, this is the length, and this is the capacity, right? The capacity of a region. Then I can allocate again, and this is after int 5000 alloc. So this is the pointer. Well, actually, I probably want to do something like this, just to be a little bit more cleaner. Add a few lines in there. I don't need that, and I want to move this below. Alright, so this is that. Here I can add a new line, and this is not going to be another printf call. Like so. Here. So this is a pointer. So this is going to be the first region. Right, so this is the first region, this is the length, and this is the capacity. Here I can say the pointer is equal to that actually, right, because I'm not going to replicate the pointer on all regions. Well, let's say int b, like so. So I can say this is A, and this is A, and I can add a second one, say int B. So we have A and B, and then I need another function call. So this is going to be that. I no longer need this pointer. I can move here this. It's going to be just 2. I can move this there. Okay, so this is the first region, and then I need something similar for the second region, and this is just going to use that. Okay, so I think this demo more or less demonstrates the behavior of the arena allocator. So let's compile it and run. I'm missing new lines, obviously, so let me add a bunch of new lines where they need to be, and I also want a new line at the end. Okay, so we have the list demo, we have the first loop, nice loose, and we have the arena allocator demo. So after int3, well, we can say like so. Right, so we can say something like that, and alloc. So it is a little bit more explicit what we are trying to say to everyone running the demo. So after we allocated 3 ints, this is the pointer of A, the first region has length 2 and capacity 512. After we allocate another thing, we have A and B. This is the first region, it remains unchanged. And then we have the second region, like so. Oh, by the way, I think I have a bug. I was editing the video from yesterday, and I think it's not a bug, but it's creates inefficiencies, because here I don't need to check equal, so I only need to check while this is greater, because if it is equal, then I can still allocate, right? Because I believe so. Yeah, because if I have basically one word and I want to allocate one word, yeah, I can do that. Okay, now I need to have another demo, so I can say custom allocators. Well, this is not really custom, this is optional allocators. And this is already going to require some stuff, because basically, well, let me first have this pretty stuff. So this is an optional allocator demo. So let's assume we have an arena, and we have something like this. So now the problem that we have with this is that we need to manually initialize the header containing the alloc function, and this is going to be arena alloc. So we have to manually do this, right? So let me first write the demo, and then I can come back and see how can we improve that. All right. So one option that we have to demo these optional allocators is to have a float list, for example. So we have our list, right? It's a float list that is going to be 0 initialized, and this list is now going to have an optional allocator, right? So I'm going to say that this is going to be a pointer to arena, right? So this needs to be the pointer, and if I don't put a pointer, this is going to complain, right? So this is going to be pointer, and I can say exactly the same thing that I said previously. So I can say this. So we are just appending floats to our list, but now we should be using the allocator, right? So to test this, we can have this. So after appending 3 floats to the list, and I don't need any of that, I can have this, and I can say that arena first region has this length and capacity occupied. Okay, so, and I can add a new line at the end. So I think this is already going to demonstrate that we are in fact using the arena to allocate these 3 floats. So we are basically using the optional allocator that we provided, right? And in this case, we are already demonstrating that we can still use the float list without providing an allocator. It's just going to use a default one, and in this case the default is malloc, but in the future it's going to be a thread local allocator probably, right? I still need to think about that. So let's run this optional allocator demo, and this says assigned to alloc. So what is it complaining about? It's complaining that this is not, so this needs to be a pointer. Oh, I think I know what's going on, right? Yeah, so we need something extra, all right? We need something extra because this needs to accept a void an allocator pointer, right? So there's only one thing I can think about, and that is to return another function, because I want this function to be type safe, right? So I can say arena allocator alloc, and this is going to be an allocator, and this is going to receive a size in bytes, right? And so the only thing that this function is going to do is basically cast this allocator into an arena. So I can say arena pointer, and I'm going to say that this allocator is in fact an arena, and then I can just return arena alloc, the arena that we casted, and the size bytes, right? So here this actually is going to be this, right? So this is going to be using the arena allocator alloc. Alright, so we can, if we do this allocator, so I need to explicitly cast it, right? So I need to explicitly cast it, probably. Can I do this? Does it allow me to do this? Demo C. Alright, so demo C. So right there. So I probably also need to cast this to an allocator. Right. So we cast allocator, and we need to use this specific function. Alright. So this should already work. It is in fact working. And from this, let me just put this there so it'll be pretty. And so with this demo, we can see that after appending 3 floats to the list, the arena first region is using 9 words out of 512 available. And that is because each single float is going to consume 1 word, right? Because we do separate allocations. Well, no, each float is consuming 3 words, and why is it consuming 3 words, right? So we can check that. So each float is consuming 3 words because each node contains a pointer that is going to be 1 word. It contains the data that is going to be 1 word, and well, this is quite strange. So let me print here. I can say size and say that the size of a node is equal to that. So I can say size of list begin, and I can dereference it. So let me go back here. So the size of an is 16 bytes, so 2 words in fact, right? So 2 words. So this is very strange. Because we should actually consume 6 words, not 9, right? So I need to understand why this is happening. So since this is the size of the node, let me move this here and have it print individually each one of those. So after append 1, after append 2, and after append 3, right? So what is this going to be the behavior? Right, so we are allocating 3 words for some reason, because because so we are here in the code, if I remember correctly, here we have size byte, so this is going to be 16. Oh, this is bytes. Oh, size of, yeah, returns the size of the byte. All right, and this is going to be 8, so we are going to have 24, and 24 divided by 8 is 3, right? So we have a little problem in here, because this is actually not correct, right? This is actually not correct. And that's why we are using more memory than we expected to use. So how can we fix this? How can we fix this? So we only want to add this padding. Well, can we add the padding afterwards? Well, but so I can say that the size is equal to this, right? And this is going to be incorrect in some cases when the amount of byte we want to allocate is smaller than a single word, right? But to check that, we can then say if size of actually, yeah, so if this times size is less than size bytes, we actually want to increment size bytes by size of a word, right? So because we can be off by a single word, never more than a word, and since the word is a minimum unit, we can check this, right? So if the size we calculated is smaller than the amount of bytes we need, then we can add a word, oh actually is plus equal, then we can add a word worth of bytes to it. I think that is probably a better formula to do this, but I can think about this in the future. I just want to test this. Alright, and this is already correct, right? This is already correct. So this is using the memory that we expected, in fact. Okay, so now I probably want to have a test for 3 again ints and alloc 5000 ints, and here I can probably do another allocation. And I can have so this is going to be B, and well actually I want this to be C, and I want to place this after the B, right? So here I want to allocate let's say a boolean or something like that, or a char, for example. So it's going to be a char pointer, one char. So after we allocate one char, this is going to be A, B, and C. So here we are going to have C. So we have A, B, and C, and this is the first region, and this is the second region. So what I'm expecting to happen is that this is going to consume a single word, right? It's going to consume a single word. It is going to allocate it in the first region because it can fit it in the first region, and it's going to ignore the second one, so it's not going to touch the second region. So that's what I expect it to do, right? So let's test it. So we allocated 3 ints, we consumed 9 words because is 9 words what we want? Oh, this is wrong because here I don't want to increment size. We need to think about this, right? Because size is in words, not in bytes. So I need to increment 1, right? Not so this is going to be size plus plus, not size plus size of, right? Because size of, it gives us the amount of bytes. We actually want the amount of words, so we need to increment it by 1 single word. That's why it was weird. So So if we test it again, okay, now it's correct. So with 3 ints requires 2 words. That's cool. 5000 ints does not touch the first region, but it creates a new region, a second region. Then if we want to allocate a single byte, the byte is less than a word, so it's going to consume a word either way. So it consumes a complete word, and it does not touch, and it is working properly, right? So this is also working properly. So the only thing last that I want to do in this episode is to handle this case, because this arena allocator alloc I don't really like, since this is required fields, right? Since this header needs to be requiredly filled or properly initialized. I have one option for now, and the add option is to create let me move this here, and then I have the arena specific functions here. We can just have arena default be a function, and this is going to return the default arena, the default values for the arena. So we can place it somewhere, probably here, and say arena results equal to this, and I'm going to say result.header.alloc is going to be arena allocator alloc, and this is going to return the results. Right, so this is the default arena, and now I can simply say arena default, and since I did this, I can probably remove this from the header implementation, the header definition, the declaration, right? So I only have arena default, arena alloc, and the generic alloc that accepts an allocator, and I think that's everything. So this function needs to be defined above this one, so it is aware that it does exist. And I think that's everything, to be honest, right? I don't think we need anything else. So this is going to be the behavior. So this is going to return me a default arena, right? And since these are options, I don't really want to define specific functions to initialize a list, because this is not required. I just specify allocator if I want to, and if I don't specify allocator, it's just going to use a default one. Alright, so if I now compile and run, this should be working properly. It is in fact working properly, and I think that's everything, to be honest. We already did a lot of stuff in this episode, and in the next episode I'm probably going to I no longer need any of these, I no longer need that, right? So I'm probably going to define pool allocator, probably, because I'm also going to need a pool allocator for my game. So I'm going to need arenas, a pool allocator, and I don't know if I'm going to need anything else, but I can handle that later. Alright, so that's everything for now, and I see you tomorrow.